Presented by Caltech.
So a quick reminder where we've been so far again. This is kind of going back to the basics again, but I think it's important because what happens today is one of those very, very key classes. A question on this is bound to happen on the final exam. It's just bound to happen. There is no way out of it. Also, this thing is important in its most fundamental way in quantum mechanics, in the theory of music, in astrophysics, you name it. Black holes, gravitational waves, everything just follows what happens here today. Okay? And this idea of standing waves is kind of crucial to this notion of how things are formed up. And we talk about the Fourier decomposition at the end of the class. So remember, we have n-coupled oscillators. Okay, again, same old story, springs, pendulas, atoms, anything. Okay? The way they interact, it's coupled. You have a large matrix, y1 double dot, y2 double dot, all the way to yn double dot. Accelerations of the n particles. The system looks like is a one-dimensional lattice of these points. Those are my points. Could be connected by springs or whatever. Pi labels the index of these points. And they're oscillating in the transverse direction y. And I'm looking at how the oscillation of these particles is changing in space and time. Like how does a wave or an oscillation is oscillating in y along x and changing in time. Okay? So like multivariate stuff going on now. Accelerations. You do Newton's laws for individual particles. Just regular good old Newton's laws. Write down a matrix, which we call M, or minus M if you want. This was an n by n matrix. Times the coordinates itself. y1, y2, so on to yn. Okay. That's our famous matrix equation for Newton's laws. And we were looking at solutions for which n was going to infinity. So large number of particles, very, very closely spaced. So delta x between particles was going to 0. And so therefore, the net length, n times delta x, was still held fixed at a constant non-infinite value, like a finite value. And the net mass of the whole chain, which was n times delta m for masses of each of these particles, was also held fixed. Okay? So macroscopically, it has something non-trivial going on. Microscopically, individual particles have almost zero masses. Okay? So I can also add delta m. So n-coupled oscillators talking to one another, everything is nice and good. Okay? We then discussed last time special solutions for that setup. But first of all, what equation does this setup obey in the large n limit? The moment I take n equals infinity, n goes to infinity, this whole matrix equation, which looks horrible, it's infinite dimensional, it reduces out in the continuum limit to something nice and pretty. So in the continuum limit, thermodynamic limit, you have partial square y, partial t squared equals the speed square, partial square y, partial x squared. What we call the physics two-way wave equation last time. In the coming homework 5, which is out now, we discussed some quantum mechanics. Same ideas, a different wave equation. Okay? And you'll realize that this question I discussed last time about a string hanging from Millikan, some of us remember that, that's on the homework. So you're welcome. You can send me flowers, chocolates, cash. All right, that's our wave equation. This is just what that matrix equation looks like in the continuum limit. Okay? It's just Newton's laws disguised. That's a wave equation. Okay? We looked at traveling wave solutions, for which a disturbance at one end propagates along x, and the solutions were of the form x comma t, where something like some function, x minus vt and x plus vt. We looked at plane wave solutions, which were e to the I kx minus omega t, speed was omega over k, the whole thing. That's so far, and that's good. We know how waves propagate on this continuum setup of particles. Could be a string in the continuum, could be anything else. Now let's look at normal modes again. Again, what is a normal mode? Remind yourselves every time, it's a special configuration of the n particles for which each has the same frequency of oscillation. Okay? So remember how in the usual sense we had x1, x2, x3 as the single oscillations, and we said, okay, x1 is some amplitude a1 e to the I omega t. x2 is a2 e to the I omega t, and so on and so forth. Every particle has the same frequency of oscillation. We demand the same thing here. What we demand is that yi on the lattice for the ith particle, as we want it to be some amplitude, let's call this ai, could be complex so that I have a phase in it. Okay? If you want to see it more explicitly, let me call this e to the I phi I. Okay, the i's got messed up. I wanted a j because, you know what I mean? Can I use an I? It'll go away in a second, so we won't need it. So this I is the complex imaginary I. This I is the labeling on the lattice. Okay, and phi I is the phase of that particle times e to the I omega t. It has some frequency omega, which I don't know yet, but I want it to be a normal mode frequency such that each particle for any I has the same frequency of oscillation. And I was just calling this real amplitude with the phase as ai tilde to condense my notation, e to the I omega t for all I. Okay. For every I, it's the same frequency for each particle. If this symbol bothers you, it's for all. Okay. All right, so that's a normal mode. Are we okay with that? Every particle, same frequency of oscillation, by definition. Okay, nothing fancy. Now, in the continuum, since I have a continuum of particles, my label I, what I was calling each particle as 1, 2, 3, 4, 5 on the lattice, that now gets labeled by where you are on the continuum. It's labeled by x, right? So I basically goes to the continuum label x. Do we all see that? N particles, I had every particle oscillating. In the continuum limit, now the particle is labeled not by its point. I don't have time to count infinite points. I got stuff to do with that, right? So we label them by a continuous variable, x, which is the direction where I'm placing my lattice points. And in that case, my normal mode solutions are now labeled by x. The I becomes the x. They of course depend on time. That's a normal mode solution. Such that the amplitudes, ai tilde, also depend on x. Now it's a function of x. Let me call it f of x. Okay? Times e to the I omega t. Okay? And this f has nothing to do with this f here. Maybe I could change it for people's peace of mind. Let's call this, I don't know, we call it g, let's call this h. Some function h of x. Question?
So you called AI, okay, wait, never mind. I was confused about it.
Sounds good. Anything else? Okay, so we're just labeling a normal mode. Every particle along the x has the same frequency of oscillation. H of x is what we're calling the amplitude. Okay, it depends on which particle you choose. If that's my normal mode solution, it's a solution to what? To my underlying laws of physics, which in this case is my wave equation. Because it's a consequence of my Newton's laws. Okay? And I'm demanding to find those frequencies, omegas, for which they are normal mode by satisfying the wave equation. Okay? So let's plug this in into the wave equation. So what do we get? On the left-hand side, I have two time derivatives. What happens here? What do I put down? I omega twice. So when I substitute this back in, I have I omega squared. Exponentials are stubborn functions, they stay the way they are. For the partial derivative, h of x is constant for the partial t derivative. So it doesn't move anywhere. Okay. So you still have y x comma t surviving, which is what you always want. Yes?
Sorry, what is the vertical line in it?
Nothing, just a separator.
Oh, okay.
All right. Equals the right-hand side, v squared, the speed squared in the medium, times partial x. When I differentiate with x, what about e to the I omega t? It just depends on time. It's a constant for the x derivative, hence stays the way it is. So I'll keep it the way it is. I have a function of h, and that gets differentiated twice with x. Okay, so this becomes the d square h over dx squared. Okay, and the y that I had on the left-hand side was also a combination of h and e to the I omega t. So let's also put that back in for explicit equation, h of x, e to the I. That's a normal mode solution plugged back in to the wave equation, my laws of physics, such that I can find omega, for which it's a normal mode frequency. Okay? E to the I omega t is cancel off, it's gone. I square is -1. So what do I have? I have partial square h, d square h, dx squared equals minus omega squared over d squared times h of x. So what I began with a partial differential equation, it was a differential equation of two variables. I have done some magic trick, and now I have a differential equation in one variable for the function h, which depends only on x. Do you all see that? This is crucial. This is actually done every time you solve a problem. This is what has to be done, like kind of blindly sometimes. Assume a solution which is normal mode, same frequency, plug it back, solve for it. Okay? So you might not have known how to solve this equation, the partial differential equation. But what about this one here? This seems much more familiar. First of all, remember the dispersion relation? Omega equals dk, that the speed was frequency over the wave number. So omega squared over v squared is minus k squared. What are solutions for this equation for h? You've seen this umpty number of times now. What equation is this? You should have this tattooed on you by now. Like, people should, someone wakes you up in the middle of the night, hey, simple harmonic equation, d squared h dx squared, just do it. The second derivative of a function is proportional to negative of the function itself. It's a simple harmonic oscillator. So, simple harmonic oscillator, and therefore, h of x, for simple harmonic motion, it's just sines and cosines. So h obeys some constant a, cosine kx, the k is the proportionality constant, plus b sine kx. Okay, this k is not the spring constant. It's a handicap of having a finite number of letters in the alphabet that you have to recycle them somewhere or the other. So I hope this is okay with everyone. This k here again is the wave number. It's the frequency over the speed. Okay? Or 2 pi over the wave number. So we solve for h. And h is a simple harmonic oscillator. That's good. And we are done. For every omega, given the speed, you can find a k, or for a wavelength, you can find the omega, for which an equation like this is a normal mode. And said in a wholesome manner, the normal mode that we were looking at was y x comma t, was h of x times some oscillatory function. I put it e to the I omega t as a placeholder for looking at oscillations with a frequency omega. Generically, it would be some sine and a cosine in omega t. Okay, so this in general would be some c cos omega t plus b sine omega t, and therefore my normal mode is therefore A sine or A cos kx plus B sine kx times C cos omega t plus D sine omega t. That is a normal mode in its all glory. Depending on space and time, it has a space part, the H, which is a harmonic oscillator. I'm looking at oscillations in time because they have to be normal modes of some frequency omega, hence e to the I omega t. I use it here as a placeholder, but a general solution for oscillation is just C cos omega t plus D sine omega t. Okay. Omega and k are connected by the speed, and this is the whole setup of the normal mode in continuum. Question for you. How many normal modes are there? One, two, I can go on. Infinity. Exactly. They have an infinite number of particles, and therefore there are infinite number of normal modes. For every omega, which is a real number, a positive real number, because frequencies are positive and real, for every positive real number frequency, this thing satisfies my equation of motion. So for the continuum as a string, without anything else, every frequency is a normal mode. And it is infinite in number. And if you're a little more mathematically inclined, I'm going to call this uncountably infinite. Why? Because you can't count the real numbers, right? You can count integers, but you can't count the real numbers. So this is uncountably infinite. Okay? So, and once we have this, we have the normal modes. Any solution, any general solution is just a sum over all of these solutions. And what is labeling my solution? My normal mode frequencies. So you integrate over all omegas of such functions, and that's a generic solution. We'll get to that. But for now, this is one normal mode. Okay? So this is a normal mode labeled by the eigenfrequency or the normal mode frequency omega. For omega, you can find k divided by the speed, and this is the mode. So take a minute here, please. Make sure we understand this. Because we'll add stuff on top of this now, talking about boundary conditions and a whole bunch of other things. But this basic idea, normal modes, when they go in, same frequency, solve for it, superharmonic motion for the H, put it together. So what you have. Yes.
Wait, what does that say? Uncountably infinite
In number.
in number?
Yes. So that in number is probably not needed, so it's uncountable. Yes.
Could you repeat the last part about like the general solution?
Sure. So this was a normal mode, right? So let's call this y normal mode. A general solution, yx comma t, which is a general solution. As we learned before, you can put normal modes together. They span the space, and any solution is a superposition of the normal modes. Okay. So this thing is just, I'll put it schematically right now. This will be an integration over omega, adding over all omegas, because but omega is a continuous variable, and you're adding all these normal mode solutions, each labeled by omega, basically. Yeah. So for each of these omegas, plug this back here, integrate, and find these constant by initial conditions, and it'll be done. We will do this, so that's why I'm not doing this in detail right now. Yes.
Do you get h of x from the a tilde n segment?
So the A tilde part was just to motivate the fact that it starts with a finite lattice. And a normal mode on the lattice is that each particle labeled by I has some amplitude times some frequency of oscillation. Now I go to the continuum. So the I becomes the x, because I was 1, 2, 3, 4 along the x direction. Now I have a continuum of particles and just labeling by the continuous variable x. You see that? So the amplitudes, which were a sub i's, now become some function a of h of x. So h is again the amplitude. I just called it h. Okay, it depends on where you are, and each particle where you are has the same frequency of oscillation.
So each one is an A, like for each given part, it is an AI of e to the I phi I.
Yes, so this part, I just had some phase involved in it. If you don't want, forget about the phase if you don't like it, I want to make it general. It's some amplitude of the ith particle and some frequency of oscillation. I just go to the continuum saying, now that I becomes the x, and h is the amplitude with the same frequency of oscillation.
Oh, so you got the solution for h of x and then plugged it in there, which has an e to the I omega t. So shouldn't there be an I like times the d sine omega because you expanded using Euler's formula?
Oh, good. So I did not expand e to the I omega t as cos plus I sine. So this is the logic here. These are just placeholders to help you differentiate, so the functions don't change. A typical oscillation, as we discussed before, a typical oscillation could be a sum of sine and cosine terms, like a sine plus b cos. So you could have started at this stage as well with c cosine omega t plus d sine omega t, and that would have stayed the way it is. This was like a placeholder for that oscillation, because I wanted to remove that from my equation like I figure out on both sides. Okay.
This is just general.
Just in general, I'm just kind of jumping a little bit here and saying, as a placeholder, this denotes oscillation. So this is not rigorous, and not from here to here, it's not a step. This is a way to solve it. You get the kind of solutions, and then you superpose them to say, this is the general solution. Okay. Sounds good. So that is a normal mode in infinite dimensions. Okay. Now the next big thing is when we couple these normal modes with boundary conditions. That will form the keystone of concepts today. So normal modes plus boundary conditions. Okay. So now, again, before we had every possible omega being a normal mode, and the string or whatever was unbounded. Now say I put some boundary conditions. Before I did not know what y is at the 0x and at the largest x. Okay? Now I'm putting some boundary conditions. Remember, my chain is bounded. The total length is fixed n delta x. Okay? I'm going to pull that down. I'm going to do this. There. Okay. We're going to use that out. Okay? That's the length of the chain, which we're going to use. It's a fixed length of the chain. And now I want to put boundary conditions on this chain at x equals 0 and x equals L. Okay? So one example of a boundary condition could be a closed boundary condition, where y at x equals 0 for all time is 0. So I take my starting end of the string and I lock it down, I fix it. The string can do stuff here, but it can't do stuff at x equals 0. Okay, that's a closed condition. And say I also have a closed condition at x equals L at the further end of the string. For all times, it's fixed again. So the string can do stuff in between, but at x equals L, the string is fixed. It's a fixed boundary condition. Okay? If that is the case, what can I say about my normal mode solutions? I have my solutions up there. I have some conditions on the solutions. Okay. If this is true for all time, this is also true for t equals 0. Okay. At the starting instant, it's also true. Okay. So let's say at t equals 0, what's my normal mode solution? Y x comma 0, which is the normal mode. Take it from up there. So this is a cos kx plus b sine kx times, what do I have? C omega t is just some number c plus d sine omega t is 0. That's 0. Okay. So just an overall constant out here. C times this whole thing. Okay. Now, what are my conditions? Y at 0 is 0. What's from my equation? This is the x part of the equation now, which is what I'm imposing my conditions on. So when I put x equals 0, a cos 0 is just a plus b times 0, which is 0. So this is just times a. I'm looking at the space part now. Okay, I can absorb this constant c into these a's and b's. This redefinition. Is that okay? Okay. So a is 0. So for a fixed boundary condition, on the left, the cos term will not contribute. What just remains is only the sine term. Okay. My second boundary condition on the left, on the right hand side, y at L comma 0 or L comma t, whatever. It's true for all times. I'm showing you for one particular time, but it's true for all times. If a were 0, this goes away. Now I have b times sine k L equals 0. So this is b sine k L equals 0. Now if b were also 0, then a and b are both zeros and there is no solution. So b is non-zero, hence the sine has to vanish. If the sine kl vanishes, kl must be a multiple of pi. So therefore kl is n pi for some integer n. And what just happened is that every k is now not possible. Before, every omega was possible, hence every k was possible, because they just have a factor of v in there. But now k is not just any old real number. It is quantized. It goes up in steps. And I'm labeling my allowed k's by kn, which is just n pi over L. Now these are my allowed values of k because of the boundary conditions. And once I have kn's, what are the possible normal mode frequencies? For each k, I have a normal mode. And omega is just kn times the speed. Okay, so this is just n pi v over L. N goes 1, 2, 3, so on. Now with boundary conditions, these are my normal mode frequencies. These are my normal wave numbers. They're again connected by the proportionality constant of v for our physics 2a wave equation. Now, how many normal modes do we have now? 1, 2, infinity. But they're not uncountable in number now. Now the number of normal modes is countably infinite. I have drastically reduced my number of normal modes. I mean, reduced in the infinity sense of words. From a continuum, uncountably infinite sense to a countable infinity. I've really brought down my degrees of freedom. So what were integrations over omegas now become summations over n, and life becomes much more simple. Okay? And this thing, this process, is what we call as quantization. And it will be the keystone of quantum mechanics next term, because you're quantizing the allowed values of frequencies. It's only allowed at these particular values of n. Okay? And these solutions, I should write this here. So for n equals 1, what does the wave look like? It's fixed here, it's fixed at L, it's just half a sine wave. Okay? N equals 2. Fixed here, it's one full sine wave, and so on. You've seen this stuff before in high school, I'm pretty sure, right? And these are what we call as standing waves. So normal mode plus boundary conditions is what we define as standard waves. Okay? Does that make sense to everyone? Okay? So that's good. What about if I have a boundary condition which is not fixed, it's fixed open. So I fix my string at x equals 0, fixed here. For the right edge, the x equals L, is a bead like free to move at x equals L. There is no restriction on this thing here. What happens then? My boundary condition y at 0x is still 0. What about the condition at x equals L? It's non-zero for sure. It's moving. It could be anything. So if I can't restrict the position, what do I restrict? Remember from last time, any boundary, think about the continuity and the force balance. Okay? So at this thing, look at the forces acting on this single bead of a particle. So think about a small mass, delta m, which goes to 0, tiny mass at the edge. What's the net force on that tiny chunk of mass? What does it have to be? Any small mass in Newton's laws, m times acceleration equals the force. If the mass is too small, but the force were non-zero, would mean the acceleration would be infinite. M times acceleration is f net. If m is going to 0, but if f net is not 0, a has to be infinite to make this a finite number. So for zero mass particles, which are physical, the net force has to balance out. Okay? Like the question in the first homework, spring, series spring, point in the middle. It's a massless point, the spring forces had to cancel out. Same logic. Okay? So the force on this particle is 0. Again, remember from the last two times, the force is the tension times sine theta. For small theta, it's tan theta. Tan theta is dy dx. So the force goes like partial y, partial x. It's like the tangent, what gives you the force. If the tangent is larger, there's a larger force. Okay? So if the net force is 0, that's a condition. That tells me that partial y, partial x at x equals L is 0. This is the boundary condition for a closed, for an open boundary condition. So getting back, I had a cos plus b sine. From the fixed condition x equals 0, a vanished, that's still the same. On the right side, I have partial y, partial x. I differentiate the remaining sine term that gives me a b cos kx times k. And this is vanishing at x equals L. Again, b can't be 0, k cannot be 0 because we're looking for non-trivial solutions. That implies that kl has to be such that cos kl is 0. And cos vanishes at pi over 2 multiples. So it's n plus a half pi for n equals 1, 2, so on and so forth. So different k's are allowed now. Again, labeled by n. It's again quantized, but it's not k l equals n pi. It's a different set of allowed values of k. On Friday, I'll do like many more examples in different setups. Today, I want to kind of get the idea together. This is very important. So it's going to be like talking about stuff today, and Friday will be more about more examples. So any questions about this stuff so far? Yes.
Why is the net force proportional to the partial y, partial x?
Okay. So yeah, I can give you a quick. So remember how let's say, had a small particle. There was a string pulling it this way, string pulling it that way. N particles connected by strings, just like what we have. We're looking at the transverse forces, right? So tension pulls you this way. If this angle is, let's say, theta, what's my transverse force? T sine theta. Okay. So the transverse force is T sine theta from here, similar to T sine theta from there. But it's T times sine theta from one of the edges. Okay. For small angles, T sine theta is approximately T theta, which is also approximately T tan theta. Because for small angles, sine theta is tan theta. Okay. And tan theta, by definition, is the derivative of the function itself. It's the slope, right? So this tan theta becomes the partial y, partial x, and it vanishes, hence this piece. Thank you. So we discussed standing waves. In open conditions, they look slightly different. They are not closed, they're closed open. So the closed points are called the nodes, which don't oscillate, antinodes. I think we know this language from before. I won't spend too much time on that because it's kind of easy to catch on. But this stuff, understanding the idea, every question will just use this thing over and over again. Okay. So once that is done, then comes the biggest magic that we're going to pull off in the entire course, I feel. Nothing is going to be more important than what happens now. So let's write down my normal modes again. This is a normal mode. For boundary conditions, so for standing waves, okay, labeled by some integer n, x comma t. Okay. I have the space part, so some number an. Okay. Just like what I was calling a here, but now I have solved for them. I know what my n's are. So every n can have a different amplitude. Who's stopping you? Every particle can have different amplitudes, right? This is the correspondence of h of x, depending on x. Amplitudes depend on where you are. So an cos knx plus bn sine knx, that's the h of x part, times cn cosine omega nt, only for the allowed normal mode frequencies, plus dn sine omega nt. Okay, a general normal mode. And a general solution is just a linear combination of these normal modes. So y, x comma t, a general solution is just summing over all these normal modes. Each normal mode is now labeled by n. So I just sum over n, yn. Okay. Now watch this closely, what happens. I have four kind of terms here. Cos kx, sin kx, cos omega t, sin omega t. Depending on the boundary condition, if it's closed, the an's are zeros. If it's closed open, then k and l is n plus half a pi. If it's closed, it's kl equals n pi. Okay. But a general normal mode looks like that, under some boundary conditions, some standing wave. Okay. And general solution is like sums over all of these. Now, what if, here is the key, I have four different unknowns here. Okay. So I must need initial conditions. Case 1 is when the string at t equals 0 has 0 speed. The speed vanishes. So partial y, partial t, the speed of the string as a function of x at 0 time is 0. So the string starts off at rest. It might have some shape initially, but it starts off at rest. Okay? What does that tell us? If I differentiate with time, this is a space part, it's all constant. The time piece, Cn cos omega nt, a time derivative becomes a minus sign, pulls an omega out. This becomes a cos, and that vanishes. What does that tell me about the C or the D's? One of them is 0 because of that. Can we see it quickly here? When I differentiate, this becomes Cn, something like a sine omega nt, plus dn cos omega nt at t equals 0. So the cos becomes a sine already goes away because sine t is 0. Here it becomes a cos omega nt, and cos 0 is 1. And that whole thing must vanish, hence d of n is 0. So if I start from rest, if my string has some shape initially, but starts from rest, only the cosine pieces contribute in the time part. Okay, I can get rid of the sine terms. On the other hand, if I had some non-zero speed, then either both or the sine term would contribute. This is a special case. Okay, if the string starts off at rest. Okay. So let's get it down after this condition. So the normal mode yn x comma t is an cos knx plus bn sine knx times cosine omega nt. Again, I absorbed the constant cn into an and bn. I could redefine and have new variables, it's just annoying and it'll make your life harder. So just realize along the way I'm absorbing constants as I go along because nothing is changing, it's just unknown constants. So a and b are still unknowns. Okay. Now, next step. Look at the shape of the wave at t equals 0. So look at how the wave looks like as a function of x at t equals 0. Initial position condition. There's some shape which is someone specifies to you. Okay. This shape is given to you. Someone starts it off this way. So this is known. Someone will tell us what this is. Okay. Let's call it some function. What do we call it? We used f, we used g, h, e, p of x. It's some function which someone has given to you. Okay. And again, this is going step by step. 0 speed, the sine term in the omega t went away. Now say I have fixed boundary conditions. So the string here is fixed as well at x equals L. For the fixed case, okay, which of the two terms is important? If it's fixed, an's had to vanish. What remains was just the sine k and x's, and kn was given by n pi over L. Okay. So under the fixed boundary condition, my function, which is known to me, I have an expansion for it. This is the new solution. So this is sum over n bn sine knx, or kn is n pi over L, so n pi x over L times cosine omega nt. This is y x comma t. I'm looking at 0 time, hence cos omega 0 is 1. This is 1. This is the shape of my wave at t equals 0. And this is a known function that someone specifies to me at the start. On Friday, I'll take up a very special case. I'll solve for this explicitly, what happens. But we should understand the flow behind things here today. I think it's very important because initial speeds, I got rid of the sine omega nt terms. Fixed boundary conditions, got rid of the an's. And quantized the kn's to be n pi over l's. So at t equals 0, I start my string in a particular shape, like a guitar string. I pluck it. It has a shape at t equals 2, which I specify. P of x is a known shape, someone will give it to you. And that known shape is expanded out in a series of sine terms. With unknown bn's, I want to find bn's. Because once I know bn's, I have solved for everything. In the fixed case, an's were zeros. The dn's went away. I just have some oscillation. If I can solve for bn's, I'll be done. Okay? And this expansion is called the Fourier expansion. I am expanding any arbitrary function in terms of sines and cosines. Okay? For lack of time today, I will not do this today, do this next time in detail. But the key is the this here that people out here we can also use this board. The takeaway, once you have this equation at t equals to 0, you can solve for the bn's. So you solve for the bn's. And that's the Fourier inversion trick. We'll talk about it next time in a little more detail. But to give out the key, this is just integral px sine n pi x over L dx from 0 to L. You find the bn's by doing this thing. Why? Next time. But known function, known signs, solve for bn's. And therefore, y, x comma t, the general solution was a sum over all possible n's. An's were 0 for the fixed boundary condition. This is for the fixed case. Bn's are given by these, so Bn's are known. Sine n pi x over L times cosine omega n. This is the general solution for a string which starts off at rest. Where did that go? Starts off at rest and has some initial shape specified by p of x. I can do a similar analysis for were the string moving or for the case where the string has some open boundary condition. The same method follows. Okay? But the bn's is what you have to find by looking at the initial shape. If this is confusing to you, that's fine. Friday we will do this like explicitly in class and see how it works. Okay? But any questions about the flow of things? Because I also want to do some like cool stuff there with the microwave. So I'm a little rushed, but yes.
Right, does this only hold when the initial velocity of the string is 0?
Yes. So this is fixed and initial velocity is 0. For most problems in this course, we'll focus on this thing only. There might be one homework problem where we might change a few assumptions to kind of give you a feel of how this is working in a more general sense, but it's still the same thing. General thing, start imposing conditions on the time part by the speed, on the space part by the shape at t equals 0. Find the coefficients by Fourier's trick, by which I need this inversion. We'll talk about this next time. There's also 2 over L here, I think. But again, we do this next time, so that's fun. Yes. And once you have the bn's by the initial shape, you're good to go. Okay? So think about more questions. Let me put up this microwave in the middle. Any more questions about it? And I also wanted to apologize for going overtime for the last many times. I realized people have classes that did not know about that. So we still have a few minutes, so hang back. So a microwave is just standing waves in application. A microwave creates standing waves. So you have nodes, antinodes, nodes, antinodes. Standing waves fixed by the microwave walls. And so you might wonder, if I heat my food, there should be some places of high heating, some places of low heating. It should not be evenly heated up. And hence in the microwave, you have this sleep tray, which rotates around. The rotation of the food makes it evenly heated. Okay? So I'm going to take the rotation part of it. I'm going to invert the tray and just put this back so it won't rotate and the little thingy won't affect me. and I'll try and melt some chocolate in the microwave. Okay? Why? Because the hope being, the microwave creates standing waves. And these standing waves have a certain form. Okay? Fixed boundary conditions, hence they look like sine waves. Okay? And we'll see if this is really true or not. So, let me get this. People here like dark chocolate or only me? I was tempted last time to finish all this off, but I survived this temptation. It was hard. So, bar of Hershey's. Okay, I'm going to put this in. It kind of broke a little bit, but I guess it won't affect things so much. And I'm going to put this on. Let's start for 1 minute and see what happens. It's not rotating. The bar is stationary. There are standing waves being formed inside the microwave. Let's give it a few seconds. What do you expect to see? Some parts completely melted, some parts just not melted. Okay, I can see it's almost got to be done. But it is. Alright, so it's hard to show. Oops. I should have practiced this last night. But you see these two places where it's melted completely and hard parts around. Okay. Okay. So I also printed a little scale. I don't have scales anymore. I got a ruler. Can someone like measure the distance between these two things? Do you want to do this? So I'm not biased. Just I know it's just moved around a lot, but so what we are doing is so the chocolate, it's melted, it's not melted, it's melted, and so on and so forth. And these are the nodes, the antinodes, the nodes, and so on and so forth. The wave is oscillating as well. So we're looking for the distance between the two melted regions of the thing. How much is it?
8 centimeters.
8 centimeters? Okay, so this thing is 8 centimeters. So how much is the wavelength of the wave?
16.
Twice. Okay, so the wavelength is 0.16 meters. Again, the chocolate moved, it's a pretty bad estimation, but in sense of it's pretty crude. Can we just like pass this on? Just see the pattern around? Don't take a bite for now. Okay, that's the wavelength of the standing wave that was formed. Now, if you look in the microwave, they specify the, okay, what do you trust more? Do you trust the microwave manufacturer, or do you trust the speed of light?
Speed of light.
You trust that more? I think that's a reasonable thing, okay? So if lambda is this, speed of light is 10 to the 8 meters per second. Can we find the frequency of the microwave? Okay, how do we get that? What's the frequency? Mu. The frequency in hertz. How much is that? Lambda, the distance or the wavelength, is the speed times time, which is speed over frequency. So frequency is speed over lambda. Speed is the speed of light over lambda. Simple regular stuff. 3 into 10 to the 8 divided by 16 into 10 to the minus 2. All in SI units now. How much is this? 3 by 16 into 10 to the 10 hertz. How much is 3 by 16? Can someone give me a number?
It's like
0.18 into 10 to the 10, okay, which is about 1800 megahertz. Okay, the microwave says 2450 megahertz. Okay, so 2450 megahertz is the frequency of the microwave. And if we do a better measurement of the distance will be slightly smaller, I think. It'll be lambda little less than 0.16. If lambda is less, frequency is more. Let's start approaching the rest of that. Okay. So standing waves are not a fantasy. They're actually being used in our everyday appliances. They are used in quantum mechanics, in astrophysics, and next time we'll do some more concrete examples in class. And I'll also talk about this very famous question about, can you hear the shape of a drum? If you have a drum, you don't look at it, just turn away, but beat it at certain frequencies. By hearing the sound, can you reconstruct what it looks like? We talk about that. So see you guys Friday.